Okay, guys. Hello again. 4 p.m. So we can start. First, a few words about the exam. I will send you email after the exam review session about which sections. But you know, I told you in the lecture that Ampere's law will be the last section. The section about the Ampere's law will be the last one in this midterm exam. Then, just now, when I was almost ready to start streaming, I realized that I need to post exam 2 from the previous year. I think I did not post it. I need to check in the Blackboard, right? If I don't post by the end of the day, send me an email, one of you. Right. Okay, so I need to do that. I just wrote it down. Right. Then, format of the exam, exactly the same. I hasn't changed it for several years. So 5 multiple choice questions and 3 big problems. Right? And again, as usual, most likely we will start earlier, right? Not at 9, but around 8:40. Right, and we will work till 8:50. But as you notice in the first midterm exam, I allow you to submit up to 9 a.m. But after 9 a.m., we'll cut it. Those who need extra time, of course, I will send you email that you can either start earlier or you work later after the class. We will communicate. Then, what else? I guess that's it, right? I don't think of anything else. Right. Again, I will I am recording everything, right? I hope everything goes smoothly. And again, I will upload to YouTube this exam review session. And again, I will send you my notes, right, as a PDF file. Okay, as usual, so if you have any questions, ask at any moment, right? If something is not clear, again, say something, right? Because I cannot check chat all the time. It kind of disrupts, right? So I cannot, at least for now, it's difficult. Okay, so if no questions, then let's start. First, I will just review major points, and then we will start solving problems. It will be about 2 hours, give or take. So, somebody's mic is on. You remember after the first midterm exam, we started looking at the electric potential, right? The electric potential, and we introduced the expressions for the electric potential created by a parallel plate capacitor, right? So if you have a negative electrode, positive electrode, of course, electric field from plus to minus, sorry. Then, when we introduce all these formulas for the electric potential, right, for a parallel plate capacitor, we introduce coordinate system, and the origin is at the negative electrode. Remember that, right? Okay, so origin at the negative electrode, and as a result, electric potential is just a product of the electric field, which is constant inside, times the distance from the negative electrode, right? Okay, so that was the electric potential of a parallel plate capacitor. Then, if you have a point charge, again, it creates an electrical aura, which can be described either using electric field E or the electric potential. They both, E and V, describe exactly the same things, right? So electric potential at distance r from the charge, r small, can be found just K, that universal constant, times the value of the charge divided by the distance from the charge. Potential can be positive, can be negative, right? If charge is positive, potential positive. If charge is a negative, then potential is negative. Then, of course, how can we connect the electric potential energy with the electric potential? It directly follows from the definition of the electric potential. We introduced the electric potential as potential energy divided by the value of the probe charge. But if you solve it for U as QV, so that's the expression which we need to find the potential energy. For example, if you position here a point charge Q, So how can you find the potential energy in this case? So you just take the value of the probe charge, not probe, charge, the value of the charge, right, regular charge, any charge, and multiply by the value of the electric potential at that particular point. So that will be the value of the electric potential energy. Right. So yeah, we used it a lot. Okay, enough. Then after that, we started connecting electric potential and the electric field, because they describe exactly the same thing, right? Electrical aura. So there must be a relation between them, right? So we established. So if you want to go from the electric field to the electric potential, it actually connects electric field with the change in the electric potential, right? So, and we derive this formula. It's a negative integral from the initial point to the final point, and most of the time we have one-dimensional case when the electric field is along the x direction. Right. So the simplified version is just the x component of the electric field times dx. So if you integrate it from the initial point to the final point, don't forget about the minus. It will give you the potential difference between the final point and the initial point. But again, we didn't use it as in an integral form. We calculated the potential difference using area under the plot. If you plot integrand e sub x versus x, right? So this is the final point, this is the initial point. If you calculate area under the plot, don't forget about minus, because it's a very common silly mistake, right? Then area with minus, or negative area, gives us the potential difference between the final point and the initial point, right? Again, we will look at the problems. And in the opposite direction, let's say if you know the electric potential V, how can we get the electric field? Again, most of the time it will be one-dimensional case. Most of the time you will have to just differentiate electric potential function, not just a number, function. It must be a function. If you differentiate with respect to x, again, don't forget about minus. It will be the value of the, it gives us the value of the, it gives us the electric field, expression for the electric field. Okay, so that's the transition. That's how we can move between the electric field and the electric potential. Okay, after that, we started moving into sort of dynamics, currents, right? When charges move, right? So, and we started preparing elements like capacitance, resistance, and so on, right? So first we introduced the idea of resistance. If you have two electrodes, plus Q, minus Q, every time the absolute value of the charge is the same, because how do we usually charge them? We just move electrons from one electrode to the other one. And of course, they will be equally charged in absolute value, but of course, opposite in sign. Plus Q minus Q potential difference delta V. As a result, we can introduce the capacitance as the ratio of the charge divided by the potential difference. And of course, we calculated, this can be applied for any object. You can calculate capacitance of any object, but when we applied it for a PP capacitor, parallel plate capacitor, we calculated that it's a epsilon naught, that universal constant, which describes electric properties of a vacuum, n times area of the plates of the parallel plate capacitor, right? And divided by the distance between the plates, right? Again, the major feature of this formula that it depends only on geometry and, of course, material between the plates, right? So if you build a capacitor, you can label it immediately, right? So it doesn't matter what's the electric field or the electric potential or charge, right? So it's sort of like an intrinsic property of that capacitor. So after that, we started looking at the method of an equivalent capacitance. If you have many capacitors, not just one.
Professor, the recording has stopped.
That's somebody started recording in the mastering physics, right? I think once.
Yes, sorry.
Yeah, so
I
don't, it's not that I don't care, right? You can start recording if you want, right? You can stop it. I record using OBS. The whole system here in my studio, right, goes through the open broadcasting system. And everything is recorded using OBS.
Gotcha.
Outside of mastering physics. I don't like how mastering physics recorded. Right? And plus, I usually also record with an external camera, additional camera. because the quality of, if you record directly with the camera, of course, better than if you stream it. Right. And then after class or after exam review session, I combine everything, all these footages. Okay, but thanks for telling me. Yeah, so method of an equivalent capacitance. And we derived all this. So if you have capacitors connected in series, in that case, we can use this formula to calculate equivalent capacitance. And the second part, that's what usually students forget. The charge in the equivalent capacitor equals to the charges in capacitors connected in series, right? Q equivalent equals Q1 plus Q2, or equals Q1 and equals to Q2, right? So charges are the same. Then, if capacitor is connected in parallel, right? In that case, finding capacitance is easy. You just add C1 and C2. And again, the second part, that's what students usually forget, right? Potential difference across an equivalent capacitor, in this case, right, equals to the potential difference across capacitor C1 and capacitor C2. Capacitors connected in parallel. Okay, so after that, we actually started introducing current, right? So if you have a piece of wire, let's say, right? So how can you introduce current? You remember, like that Boston Marathon example, sitting by the road and counting runners crossing imaginary cross-sectional area. Exactly the same with current. So if you sit here, imagine cross-sectional area across the wire with current, and count electrons crossing, basically amount of charge crossing your imaginary cross-sectional area. Of course, looking at the watch, right, counting time. Then if you take the total amount of charge, which you count, and divide it by the observational time, that's the current, right? And if dt is infinitesimally small, observational time, then current is instantaneous. Or you can introduce average current if you measure charge over finite period of time. Okay, then, if you have a piece of some conductor, right, and if you apply potential difference, of course, there will be some current flowing through this conductor. So in this case, you can introduce what is called resistance, right? Because any piece of conductor has some amount of resistance. If you take potential difference divided by the current, so that's how we introduce resistance, right? And if you have a resistance of this resistor of this shape, right, some kind of like a cylinder, right, of some cross-sectional area, some length, right, made out of certain material. In this case, we can calculate resistance as resistivity, which is a constant describing that particular material which is used to build this capacitor, to make this capacitor. Then multiply by the length of the resistor, conductor, and divided by the cross-sectional area. Again, the major feature, like in this formula, that it depends only on geometry and the material. It doesn't matter what's the current, what's the potential difference, what's the charge. Resistance is sort of like an intrinsic property of a resistor over conductor. Right? Conductor also has some resistance, amount of resistance. Okay, then we introduce current density. Simple, current divided by the cross-sectional area through which that current flows. Then, of course, we introduce power, right? The amount of energy transformed, dissipated by the electrical element, right? So current times the potential difference, or we can rewrite it in terms of delta V squared over R, or I squared times R. Using Ohm's law, you can easily move between these formulas. So now, so that's how we can describe one resistor, but if you have multiple resistors, and first we'll look at the special case when the resistor is connected either in series or in parallel. Right? So in case of a resistor is connected in series, finding equivalent resistance is very simple, R1 plus R2. Right? And again, this piece of physics, which students tend to forget, current flowing through the equivalent resistor, I equivalent, equals to the currents flowing through the resistors connected in series. Right? IR1 and IR2. These three currents are equal. Then, in case of them connected in parallel, finding R equivalent I don't like this formula. Right? 1 over R plus 1 over R, right? And potential differences. Potential difference across an equivalent resistor equals to the potential difference across resistors connected in parallel. Okay, so that's how we can analyze resistors connected in series or in parallel. But what if they are not connected in series or in parallel? In that case, we can use Kirchhoff rules, right? Because they are universal, because basically it's a conservation of current and conservation of charge and conservation of energy. That's what lies behind them. Right? So there are two of them. Junction rule. If you have a junction point, the total amount of current entering junction point must be equal to the total amount of current leaving that junction point. And then loop rule. If you take any loop in a circuit, it doesn't matter which loop, and if you walk around in a certain direction, counting all the potential differences across each element in that loop, when you get back to the initial point, your sum must be equal to 0. Sum of all the potential differences must be equal to 0. So we will practice that again. Then after this, we looked at the RC circuits. I didn't write down the formulas for RC circuits, right? But exponential decays and time constant, just now I realized, right? And time constant can be found by multiplying R resistance and the value of the resistor and capacitance, right? RC, time constant, and all the functions have an exponential decay. We usually talk about discharging most of the time a capacitor. All right, but we will look at one example. Then after that we move into magnetism, very fresh, just a couple of classes ago. So, and we introduce Biot-Savart law, first universal law in the world of magnetism, and we introduce it for a current. So if you have current if you have a wire with a current I, right, and let's say you want to find magnetic field at that point P, which is at the distance R from some infinitesimally small section of the wire, right? And we introduce the unit vector, which shows a direction to the point in question. And then we can find contribution to the net magnetic field at that point from this ds, right? So mu naught, new universal constant permeability, right? Which describes basically magnetic properties of vacuum. Right? It's like epsilon naught, electric properties of vacuum. This is magnetic properties of vacuum. They sort of play similar role. Right? For pi, the value of the current, and then cross product ds cross r. R hat, it's this unit vector, right? So the value of r hat, 1. And divided by the square of the distance from ds to the point where we want to know the magnetic field. Okay, then if you apply this formula for an infinitely long straight wire with current I, right, we know that magnetic field lines are circular. We can use right-hand rule number 2 to find the direction of these magnetic field lines. Outstretch your thumb in the direction of the current, and your curled fingers gives you direction of the magnetic field lines. And the absolute value of the magnetic field at the distance r, which is perpendicular, or the shortest distance from the wire to the point where you want to know the magnetic field, the value of the magnetic field. So mu naught I divided by 2 pi r. So meaning of r here, meaning of r there, completely different. Right? It happens quite often, and right. And then the last piece. Just recently, we introduced Ampere's law, and in my sections, I will still look at one example in our Monday recitation classes, because I didn't look at that example, which I assigned. So, integral over a closed loop, which we called an Amperean loop, of dot product B dot ds equals, again, our universal constant mu naught times current enclosed by a chosen Amperean loop. So that's what will be, that's the scope of the material which will be on the exam. And so now, let's start looking at examples. I prepared about 8 problems, give or take, right? We'll see how it goes. Some of them shorter, some of them longer, right? And I will be using this part of the whiteboard. I hope it will work. Okay, so far so good. So we just discussed. And now let's start from the top with this electric potential energy, right? So let's assume that we have what? A PP capacitor, a parallel plate capacitor. Okay, so let me put a first bullet, so first problem, or maybe I will write number 1, right? Most likely then I will lose count. And we have a parallel, okay, I will just grab it because it will be easier. So we have a parallel plate capacitor. All right, so let me, should be enough. Right, and we know that, okay, the problem gives that electric field points this way. And the value of the electric field is given. So the electric field this way. Right, so E. And the value of the electric field I will write in a second. Immediately, which slightly overexposed. Let me move the soft box slightly further away. Still, okay. No. It's still visible. Right. So immediately we can tell which electrode is positively charged, which electrode is negatively charged, because you remember electric field all the time points from plus to minus. So this is a positive electrode, and of course this is a negatively charged electrode. Right? Then distance between them is given. So let me start writing. So we have first of all a parallel plate capacitor. Right. Distance is between the plates 40 millimeters. It's a reasonably big distance, but it means that plates must be reasonably big. Right. Okay, electric field, the value of the electric field strength. Again, guys, recently in one of the exam or in one of the office hours, right? I noticed that students, some students, right, don't realize that if problem says electric field strength or magnetic field strength, it means its absolute value, magnitude of the electric field, right? So you need to understand the language, of course. So electric field strength is 12,000 newtons per coulombs, or volts per meters. It's the same, right? Then we have an electron which is shot from the It's actually opposite direction. Electric field is in opposite. Let me change it, right? I don't like. Okay, sorry. I don't know how they look, right? It's not a big deal, right? I can easily adjust it. Okay, so electric field points this way. And then, of course, this will be negatively charged, and this will be positively charged. Okay, plus. And it's important to emphasize on one piece, which will be later, right? So minus. Okay. All right. Then, what else is given? Initial velocity of an electron. So we have an electron, E minus, right? And initial velocity is 1 times 10 to the power of 7. Initial velocity, and as I said, electron is shot from this point here. So this is an electron, and this is the initial velocity V0. So of course, what is this electron going to do? Of course, it will be attracted to the positively charged plate, so it will be decelerating, right? So sooner or later, right, it stops and starts moving in the opposite direction. So this is our initial point, right, and this will be our final point. So in the final point, velocity is, of course, v final. It's a turning point, so velocity is 0. Okay, so what else is given? Okay, so what we need to find? We need to find the distance of closest approach of the electron to these negative electrodes. So basically, we need to find S final, right? Let me write, so, okay, I wanted to write S, but I haven't introduced coordinate system. So let me first introduce coordinate system, and only then I will be able to write what needs to be found, because I don't want to write the whole sentence. It's too much, right? And how do we usually introduce coordinate system for a system like this, for a parallel plate capacitor, right? You see, you remember, the origin is usually at the negative electrode, right? So let's do the same, because all the formulas were derived assuming that. So, and now you see a negative electrode is over here, so I will introduce my coordinate system that way. And pretty much because of this point, I didn't want to flip the electric field. I want to emphasize on this point that origin is at the negative electrode. Okay. Right, and so this will be our final point. This will be our S final, and this is our S initial, right? So what's the value of S initial? Since the origin is over here, so S initial is D. S final, that's what we need to find, right? So S initial, okay, it looks more like delta. S initial equals to D, and S final, that's what needs to be found. So the problem, we solved something similar, right? But that's the review. We're just reviewing what we've done like a month ago. This problem can be solved using two approaches. Force approach, energy approach. In this case, they're equally easy or equally difficult, right? But equally. Right? But since we are reviewing this energy approach, so let's look at the energy approach. So we're going to use, of course, energy approach. And of course, if problem says use energy approach, please use energy approach, because if you use different approach, yeah, it's not going to be good. Okay, so what energy approach is based on the conservation of mechanical energy, right? So straightforward. So it just means E initial equals to E final, right? So that's the beginning, starting point, which we used all the time using energy, before we start using energy approach, right? And then, of course, we can write, so Q initial plus U initial equals K final plus U final. Again, K, kinetic energy, U, potential energy, right? So what can be dumped immediately to simplify this? In the final point, final velocity is 0. So kinetic energy at the final point is 0, because kinetic energy is 12 mv squared. So this, let me allow me to dump this immediately. Right. Our unknown is in one of these potential energies, right? So this is, okay, velocity, initial velocity is given. Right. So let me probably I will write like this, right? So K initial equals, I will combine these potential energies on that side, U initial minus U final. And now we need to connect it to the first electric potential. How can we connect potential energy with the electric potential? QV, right? So over here I can plug U equals QV. But in the problem right now, potential energy is, the electric potential is not given, right? Electric field is given. But can we find electric potential if the electric field is given in the parallel plate capacitor? Easily here. All right, so if you know the electric, the value of the electric field, right, you can find the electric potential at any point inside of the capacitor. If you know, of course, at which point you want to find electric potential. So V equals ES explanation box. And so as a result, U equals Q E S. So that's what we are going to use here instead of these potential energies, right? So as a result, I can start writing explicitly mv naught squared. Again, it's a mass of the electron because we are shooting electron, equals Q E S final minus Q E S initial. Our unknown is here. Charge, of course, is given. Charge of an electron. Electric field is given. S initial, at the initial moment of time, the electron is here, which is D, right? So near a positive electrode, and according to our coordinate system, it's at the distance D. So this is D. Okay, so what? Everything is given except for SF. So we just need to find it, solve it for SF. So which way? I probably just, yeah, I will factor out QE, move it to this side, right? So it will be mv naught squared over 2 QE, and it will be equal to SF minus, okay, let me write immediately D, minus D. So I just factor out Q times E on the left, on the right-hand side. And I can move downstairs to the left-hand side in the denominator. Right? And that's our unknown. So of course we can solve it for SF. It will be equal to D plus mv naught squared over 2 QE. It looks for now strange. Like if you look quickly at this. Why? Because SF is definitely must be smaller than D. Because everything happens between the plates. And the distance between the plates is D. So S final must be smaller than D. But it looks like here we're adding something to D. Are we adding something? Or are we subtracting? The charge. It's a charge of an electron, negative value. So the negative value of the charge gives us minus in front, and as a result, we will be actually subtracting this value from D. So SF will be smaller than D, as it should be, right? As it should be. Right. Okay, so let me emphasize on that. So this is equal to minus 1.6 times 10 to the power of minus 19 coulomb. Again, emphasizing on the minus. Right. So as a result, I'm not going to plug numbers. Right. I will just write the answer. Right. So D is 40 minus, okay, let me write, so 40 centimeters, wait, millimeters. Right. Yeah, millimeters. All right, minus, okay, I converted to 22 millimeters, 23.7 millimeters. It will be 16.3 millimeters. Okay, so usually so far, most of the students don't have significant troubles with problems like this. Sometimes some of the students get stuck when they have to connect electric potential energy with the electric potential, but not much, not many. Okay, is it good? In my notes, I also solved this problem using force approach. You can look if you want, right? But of course, force approach is not going to be on the exam. Then there is another problem similar to this, but different. Again, you can practice by yourself if you feel like. Again, there is an energy approach and force approach. Let me stand on this side. All right. And also another, which is kind of a little bit easier. Again, you can review it by yourself. You can look it by yourself. Right? The idea is, again, very similar. Again, conservation of mechanical energy, kinetic, potential. Potential energy is connected to the electric potential. So exactly the same idea, but the problem is slightly different. Okay, so now after that, of course, with the point charge, similar idea can be used with the point charge. We played with the capacitor. Now let's try to move between these two quantities, electric field and the electric potential, V and E. So let's solve one problem about that. Okay, I will start erasing this.
While the race is run, today belongs to them, the women and the men, the athletes standing proud and tall. The triumph and the tears, the sacrifice of years, they come today to risk it all. And in the distance, the stadium
So,
beats like a
number 2. So what is in this situation? We have information about the electric field, E, in the x direction. Again, one-dimensional situation. Information about the electric field is given in the form of a graph. Probably I will draw it here. So let's say this is our EX in units, now volts per meters. Usually in the problems like this, it's easier to use, more convenient to use volts per meters. In the previous problem, we used newtons per coulombs, but again, it can be easily shown that newtons per coulombs, it's the same as volts per meters. Right. And versus x. Right. And the graph has this shape. Just a straight line. We have a very nice graphs so far, all the time, usually straight lines. Or parabolas, occasionally, not very often. All right, and what is given? So we have this, okay, this is 0, x equals 0. This is 0.1 meter. X is in meters. Right. Probably I should have emphasized, so x is in meters. And at this point, the value of the electric field is 500 volts per meters. So then additional piece of information is given that okay, let me use the right. So at the origin, the value of the electric potential is 50 volts. Again, this is information about the electric field. But we also know that the electric potential at the origin is 50 volts. So we want to get the function. How does the electric potential changes with x? Right? We solved similar in the lecture, right? So let's just refresh it. Right, so what is given? A graph. What needs to be found? We need to find how V changes with x. And again, I will emphasize function. So we want to find function. It's slightly more difficult than finding the value of the electric potential at a particular point. Now let's find function. All right, again, so we want to move from the electric field to the electric potential. Let's see which bridge has to be used. Of course, the first one. So that's the transition from the electric field to the change in the electric potential every time. The first formula connects electric field with the change in the electric potential between the initial and final point, whatever your final and initial points are. Right. Okay, so let me separate it and rewrite first of all the formula. So delta V equals minus integral from x initial to x final Ex dx. Right. Immediately I adjusted it for one-dimensional case like what we have in our problem. So first of all, again, this is basically like universal. You can apply it for any electric field, for any initial and final points, no restrictions, right? It's just a universal formula connecting these two quantities, right? So first of all, we need to decide which point should we take as an initial point and which point initial, and which point should we use as a final point. It depends what is given in the problem. Since problem gives us the value of the electric potential at the origin, it makes sense, of course, to use that point as the initial point. So x equals 0 is our x initial. And then, which point should we take as a final point? Again, usually in the lecture when I ask that question, most of the students pick just x equals 1. But if we pick x equals 1, in this case, look, delta v, it's a v final minus v initial. The value of the initial point is, x equals 0. But final point, if you pick x equals 1 as your final point, in that case, you will be able to find the value of the electric potential at that particular point only. You will know the value of the electric potential at this point. But the question is, find the function. So it means that in order to get the function, our final point must be some arbitrary point x, So let me write arbitrary x is our x final. But again, if the question was about finding the value of the electric potential at point 1 or point 2 or whatever point, in that case, of course, you would take that particular point to find the value of the electric potential. So now after that, we can start writing explicitly. So this is v final, v at x, right? Then minus a v at x equals to 0, that's our initial point, right? And equals to negative integral of ex dx from 0 to x. It's the initial point, that's the final point. So let's show on the graph where that final point, for example, here, let me write, so this is our x, right? Our arbitrary point x. Right? And so we're going to use that trick which we used. We're going to use area to calculate this integral. Negative area, minus in front, so it's a negative area. So it will be minus area. Which area? So let's see. So this is our final point. So this is our Vx, right? So we need to find this area. So of course, area of a triangle, let me label it. This point is what? O. This point, let's say A. And this point, let's label it B. A and B. Area of a triangle. OAB. OAB. Okay, so we know how to find area of a triangle, right? So it will be negative minus 1 over 2. The base, x, right? X minus 0, it's just x, this length, right? X. And then now we need to know this height, of course, AB. In order to find that height, we need to know the formula for this line. Right? It's a straight line which goes through the origin. So there's no free factor, so it just must be some constant k, which is the slope, the value of the slope, times x. Right? So the slope is, we can use this point, right? At 1 meter, the value of the potential, 500. So the slope is 500. So the equation of this line, let me write it here. So y, okay, not y, damn it, it's a v, force of habit. All right, so Ex equals 500x. So that's the equation of this line. As a result, the height, right, it's at point x, so it will be, the height will be 500x. Okay, so let me write it. So this is 500 times x. Okay, so base is x, height 500 times x. So let me write it here. 500 times x. Almost done. The value of this at V at x equals 0, it's 50 volts. So let me remind this. So this is 50 volts. Right. Okay, let me first rewrite it one more time. So let me move to that side with plus. So V at x equals to V at x equals 0 minus 1 over, okay, I can immediately divide it. So it will be minus 250 x squared, right? And the value of this, yeah, it's a 50 volts. So as a result, function is 50 minus 250 x squared. Right. We've done very similar in our lecture, not recitation class, lecture. Right. So that's the answer. But again, if the question was about finding the value of the electric potential at a particular point, final point, use that point as your final point, and in that case, of course, you will get a number, not the function.
Where did you get the 250x squared?
Here. You see this line? Negative. You see I calculated area of a triangle. So minus 1 over 2x, 500x. I just cancel, right? So this is, and this, it will give us 250, right? If you divide 500 over 2,
Yeah.
you will get 250, right?
Yeah.
Yeah, okay, so that's the origin of that. And minus in front, so it's minus 250 x squared. X here and x there, right? Make sense? Okay, I hope it is, right? Okay, so anything else? Again, the first part I solved, I found the value of the potential at a particular point, and then the second part I found the function. Right? Again, you can look if you want to practice that. So this is quite simple. All right, I'm not going to discuss it. It's how to move in the opposite direction. So there is a plot how V changes with X, and basically in order to find information about the electric field, look at the slope and don't forget about the minus, right? So find the slope. Usually most of the time it's a straight line. Find the slope. Everyone can find slope here, right? And don't forget about minus. Again, typical mistake, silly mistake. Students forget about minus. Once even I forgot about minus. And I don't remember where, several years ago, there was a situation. Okay, and now this, my all-time favorite question, right? Let me again repeat it. But of course, much faster. And also, I will give you sort of the easier way of looking at that problem.
Today belongs to them, the women and the men, the athletes standing proud and tall. The triumph and the tears, the sacrifice of years, they come today to risk it all.
Professor?
Yeah.
Sorry, you erased the last line. Is the 50 negative?
No, the value of electric potential is positive at the origin. It's given, right? Of course, the problem might be stated, I don't know, 0.
But are you subtracting that?
No, not subtracting, because over here, you see, I haven't erased it completely, right? So V at x equals 0, right? And it was equal negative integral, right? So you see, it comes from, because the formula is delta V, right? Delta V. And that's what I wrote, delta V. It's a V at final point minus V initial. Delta V every time it's a final value of something minus initial, minus. Because it comes from delta V. So on this side, on the left-hand side, the value of the potential at x equals 0 is negative, right, with minus. But then, of course, now I started solving, I moved this term, which is negative, to the right-hand side with plus.
Okay.
Make sense? Yeah, again, it's another mistake. I mean, another place where some students make mistakes, right? If they're not very careful, right? So be careful. Yeah, because here minus comes from the delta. And then if you move to the other side, it becomes positive, and so just the value of the potential which is given in the problem. Right? Cool. Right, so let me erase that finally. And this, it will be number 3 as far as I remember. So you remember that if you have the information about the electric potential, right, so let's say V, it sounds silly, but it's an electric potential and the units of volts, right? Then X, and the graph is, in this case, given this way. You remember this type of problems. Right. And again, we have an electron released at which point? Let's say this is 1, this is 2, somewhere here 3. So released at X equals 2, let's say meters, units of meters. It's not really important, right? So the electron is here. So that's our, where should I write? Let me write it here. So electron. And you remember the question. We solved these questions a couple of times, similar. Right, I just wanted to give you also the easier solution, or easier way of getting the correct answer. All right, so we discuss it in this way. So first I created like a train of thoughts from the very end and to the very beginning. So we need to get information about direction, right? So let me repeat it. Direction. Right. Is it going to move to the left or to the right, with acceleration or without acceleration, right? And so since we are interested in the direction of motion, right, so it's kinematic, so usually information about the direction we can extract from the velocity. If we know direction of the velocity, that's 100% direction of motion. No doubts. Velocity that way, that's direction of motion. Velocity that way, that's direction of motion. But in our case, initial velocity is 0. It is released. Oops. Right? So immediately that information is lost. So if we cannot get from the second level of kinematic parameters from the velocity, you remember first level position, distance, displacement, second level velocity, and the third level acceleration. So we're diving deeper and deeper and deeper. So if you're not getting information about direction from the velocity level, it means that you need to dive deeper into the acceleration. And in this case, acceleration, since initial velocity is 0, acceleration does give us direction of the motion, right? Because initial velocity is 0. You remember I gave you this example. If you drive the car and velocity is not 0, let's say 60 miles per hour, and if you press the brake slightly, you still move forward, but your acceleration is opposite. So acceleration doesn't give us direction of motion all the time. But since initial velocity is 0, then acceleration does give you direction of motion. Like if you're standing in the car, initial velocity is 0, and then whatever your direction of acceleration, you accelerate that way, you accelerate that way, you accelerate this way, that's the direction of motion. You accelerate in the opposite direction, that's the direction of motion. So in this special case, special situation, yes, direction of acceleration give us direction of motion. So A. Then, of course, so how can we get information about acceleration? Using Newton's second law from the force, right? F equals ma. Oops. Writing too many electric fields recently. Ma, right? Then, in order to get information about force, of course, it's electric force, right? The nature of this force. We need to know information about the electric field, E. And of course, how can we connect them? Force equals QE, right? And then, since we have information about the electric potential, of course, we can connect the electric potential, here, electric potential, and the electric field, right? So this bridge in the opposite direction, right? So of course, from the electric potential, we can get the information about the electric field, again, using that formula. So E equals minus dV over dx, right? So that's the skeleton of the problem, which I offered to you like a month ago. Right. So let's quickly repeat it. So dV over dx, as I said, is just a slope. So electric field is just a negative slope of the electric potential, of the graph, electric potential versus x. So the slope at this point, slope is negative, obvious, right? Obviously. And slope is negative and minus in front, so the electric field will be positive, right? So let me say, so this is negative and minus in front. So as a result, electric field is positive. So electric field points this way down the hill, right? So electric field. So electric field that way. It's already underneath written. Right. So now we know electric direction of the electric field, and then of course, in order to find force, Q times E. And since we have an electron, which has a negative charge, right? So let's show that this is negative also. Negative. So if electric field points this way, negative sign of the charge is going to flip direction to the opposite to get direction of the force. So force will be this way. So this will be force, electric force acting on this charge. So force is that way. And then after this, since mass positive all the time, mass cannot be negative, right? So direction of the force give us direction of acceleration. So acceleration also this way. And then, of course, as we discussed, in this case, since initial velocity is zero, direction of acceleration give us direction of motion. So this way. Okay, so it's a long way, but again, I like it because you have to use almost everything, right? But easier way, this way. You remember when we introduced current? Current, it's a motion of which charges? Effective motion of which charges? Positive, right? Although we know electrons move, positive charges don't move in current, right? And so, but anyway, we can do that, right? Mathematically, it's okay. If positive charges move this way, it's like a negative charges moving in the opposite direction, right? So anyway, current, it's a direction of positive charges. And current flows from what? From plus to minus, from positive electrode to negative electrode. So it means, and of course we all know that positive electrode has higher electric potential because it's positive. Any positively charged object has a higher electric potential because the potential is just positive. And any negatively charged object has smaller electric potential because it's negative. So positive charges flow from areas with higher potential, from plus to minus, from areas with higher electric potential to the areas or regions with lower electric potential. So positive charges all the time flows from areas with higher potential, here higher potential, to the region with lower potential. So the potential goes down. So positive charges, if we had a proton, it would move this way. But that's for positive charge. What would be the behavior of a negative charge? Of course, it would move in the opposite direction, right? Of course, negative charge would move that way, and that's what we established, right? So if you think about positive charges, finding direction of motion of a positive charge using idea of current, then negative charge, of course, will be in the opposite direction. So it's easier way. This analysis is easier. Right? But again, I like this because of the structure. And because we have to use plenty of stuff, which we discussed before that point.
If the electron was released on that positive slope there, would the electric
of course,
field
behavior would be different. Behavior would be different. Right?
Okay.
If positive, you said electron. If electron would release over here, if we use the last approach which I gave you, again. Positive charge, let's start with the positive charge. Positive charge, of course, would move again from areas with higher potential to the areas with low potential. So the positive charge would move that way, positive, if it was a proton. But of course, negative charge would flow in this direction, opposite direction, if it was released over here. Right. Make sense? Or you can run again this analysis exactly the same way, but the difference would be if an electron were here, released here, dV over dx would be positive, right? because here the slope is positive. dV over dx positive, but minus in front. So it means that the electric field would be not that way, but this way. Electric field would be that way. Then force, because the charge is negative, force will be that way. And then, of course, acceleration that way. And the direction will be that way. So, of course, opposite way. Yeah, make sense?
Yep.
Okay, awesome. Okay, enough of this. Oh my God, now I've come to the point where it is going to be long one. Maybe I will have to make 5 steps. But anyway, let's do it. So we finished with this. Capacitance, I didn't feel like playing with that. So now let's play with R equivalent. And I'm not going to discuss C equivalent because ideas are very similar. Very, very similar, right? Except for, yeah, you need to remember what is constant, right? But sort of philosophy of the problem, ideology of the problem are extremely similar for this case and for that case. So this time I decided to discuss R equivalent, and of course there will be a problem about C equivalent. How I'm going to fit it, I need for this problem bigger board. So that was number 3, now it should be number 4. Again, if I'm counting it right. So let's assume we have this circuit. Okay, I will grab it because it's difficult to every time look down. Okay, arrange your page like this, right? Okay, if you have yeah, you do have a white page, right? Of course, you can start from here, and we're going to draw circuits. And of course, you can leave some space above or below. But I'm going to arrange my diagrams like this, from the top to the bottom. And I'm going to write something on the right side, and then something on this side, on the left side of these diagrams. So I guess I will need less space over here, more space there. Right. So we have a battery first. Then I have a resistor, first one. Then there is a resistor over here. Then I will split this into 2 parts, and there will be 2 resistors here. Right. Then I will connect this battery to this part. Then I will go to here and I will introduce another resistor, and then it goes to this point, and everything is connected like this. Okay, there must be 5. 1, 2, 3, 4, 5. Yeah, 5 resistors. Now let me label them. And so, okay, again, I need to look at my notes often. So this is R1, 8. Okay, I'm not going to use units because I'm sort of starving for space. 8 ohms, of course. Right. Then R2, this. Okay, let me write this way. So R2, 6 ohms. This is R3, 12. Okay, it's overlapping a little bit. Let me rewrite it. 12 ohms. Then these are 4 ohms. This. And R5, this is 2 ohms. Right. Okay, and the potential difference across the battery. So this is, let me write again vertically, delta V, 24 volts. 24 volts. Whew. Right, so we need to analyze it. So what does it mean analyzing? Circuit full of resistors, find all currents through all of these resistors and the potential differences. And we solved something similar in the lecture, right? But let's review it, refresh it. So first, again, you remember idea. We need to simplify this circuit to the simplest possible, where you have one equivalent resistor, one equivalent resistor, because we will see all of these resistors are connected either in parallel or in series. Right? Of course, if they're not connected like this, then of course we cannot use this method. But in this case, everything is fine. And then once we simplify the circuit, then we will start going back, finding all values that need to be found. Right. Okay. So first, I will probably start looking. So R3, this one, and R2, obviously connected in parallel, because potential difference across these two resistors stays the same. It doesn't matter how you drive this circuit. If potential difference stays the same, those elements are connected in parallel. Right? So these two guys, right, are in parallel. So as a result, I will make a transition from this circuit to the next one, and this case is parallel transition, right? Parallel. And let me redraw the circuit. All right, there will be lots of redrawing. Right, so R5 stays the same, right? So R5. Then this stays still the same, R4. And instead of these two guys, I'm going to introduce R2, 3. Since I am replacing resistor R2 and R3, so equivalent I labeled as R2, 3. It makes sense, right? Then R1 still the same, untouched. R1. And the whole thing is connected over here, right? Yeah. So now, first equivalent circuit. And so let's find R2, 3. Resistors connected in parallel, so we need to use these reciprocals, 1 over R, 1 over R, 1 over R. Right? So I will write it here. So 1 over R2, 3 equals 1 over R2 plus 1 over R3. So 6 ohm and 12 ohms. I'm not going to calculate. You can easily do it, right? Or you can look at my notes. I will send you my notes. I will just write down the answer, right? I'm not. Of course, you can bring to the common denominator and then flip it, right? So I will just write down the answer. So in this case, R2, 3 equals to 4 ohms. Right. Okay, let me circle it because I will need it, of course, on the way back. So now, out of these 4 resistors, obviously now, so the next step is these two guys, R4 and R2, 3, are connected in series, right? So the next transition will be from here to there, and these guys connected in series, right? So now, of course, I have to redraw. Of course, still the same delta V potential difference. So now, the same battery, okay, the same R5, right? We still didn't touch it. Then, instead of R2, 3 and R4, I'm going to introduce an equivalent resistor R subscripts 2, 3, 4. Logic is clear, right? So let me write. So this will be R2, 3, 4. And R1 is still untouched, right? So R1, and that's our equivalent circuit. The next step, right? R2, 3, it's trivial, you just need to add, right? So if resistors connected in series, we just need to add their values, right? So R2, 3, 4, it's R2 plus R2, 3 plus R4. Right. So R4 was, where is my R4? 4 ohms plus 4 ohms, 8 ohms. So R2, 3, 4, 8 ohms. Again, let me frame it, right, so I can easily spot it. So the next one, so these two resistors obviously connected in parallel, right? So the next step will be parallel, right? They're connected in parallel, right? So let me redraw the circuit. R5 still there. And now instead of these two guys, we will have R. Now we have 1, and we're going to combine with 2, 3, 4. So it will be subscript 1, 2, 3, 4. R, 1, 2, 3, 4. And the value of that R, 1, 2, 3, 4, it's a parallel, so we need to. Right, 1 over R, 2, 3, 1, 2, 3, 4 equals to 1 over R, 2, 3, 4 plus 1 over R, 1. Right. Again, you can calculate. Its numbers are very nice. So the value of this R, 1, 2, 3, 4 is going to be 4 ohms. Again, let me frame it. In the last step, of course, these two guys connected in, obviously, series. Right, so these guys connected in series. And so we're getting the final, the simplest possible circuit. All right, so the same battery, and now we have finally R equivalent. Right. And still the same potential difference across the battery. So R equivalent, of course, it will be R5 plus R1, 2, 3, 4. So R5, 2 ohms. R2, 1, 2, 3, 4, 4 ohms. So 6 ohms. 6, let me check. Yeah. So 6 ohms. Okay, so that's, yeah, we're almost at the in the simplest circuit, so I don't have to remember. I need to use it now. So now at this point, yeah, can we find something about this circuit? At least something. At this point, yeah, trivial. We can find the total current provided by the battery. Right. So again, you remember when we do this, all these replacements, the rest of the circuit must work in exactly the same way. So it means that battery must work in exactly the same way, the same potential difference, the same current. In all these circuits, current must be the same, right? So if we find current, then of course that will be the current even in this original circuit. So at least now we found something. We will find something, and then sort of like creating a crack in the wall, and then you can start making that crack bigger and bigger, finding the rest, what needs to be found. So let's find I equals, so delta V divided by R equivalent. So delta V is 24 volts divided by 4 amps of current. So 4 amps of current. So we found current. And now, after this, yeah, we can start going back, restoring the original circuit. Okay, I will use probably blue now. No, red for bridge. So now, going back from this circuit to that circuit. So which bridge do we have to use? Okay, this resistor replaces these two resistors connected in series. What is the same for these resistors in this case? In series, current. Current in the equivalent resistor equals to the currents in resistors connected in series. And we know the current in the equivalent resistor. So that's the first bridge. To go back, so let me write, so the bridge will be I equals to I 5. You know what, let me erase bridge. I'm starving for space, and I'm wasting it like this. No way. So I equals to I5. So I, it's a current in the equivalent resistor, right? It's this current. And then I5 and I1, 2, 3, 4. I1, 2, 3, 4. And the value of this current, of course, 4 amps, which we just found. Right, so that's the bridge which we need to use in order to make the first step. So as a result, we know the value of R5. We also just found the current in R5, 4 amps, so we can find the potential difference. Sorry. It's the first parameter which we will be able to find. Potential difference across the resistor number 5. Right, so let me use blue. So delta V5 equals to I5 times R5. Again, I5 comes from the bridge, right? And so we can find now potential difference easily, right? So I5, 4 amps, R5, 2 ohms. So 4 times 2, 4, yeah? Yeah, 2, and this is, 8 ohms. I mean, 8 volts. 8 volts. So at this point, we can say we know everything about the resistor 5. We know the current. We know the potential difference. R5, done. But inside of R1, 2, 3, we still have tons of hidden information, so we need to reveal that, the truth, right? So now let's find the potential difference across 1, 2, 3, 4. Of course, it will be current across 1, 2, 3, 4 times the value of resistance, resistor 1, 2, 3, 4. So current again from the bridge, just 4. Right, so let me write. So it's a 4 amps times, and the value of the resistor, it's over here again, 4. 4 times 4, 16 volts. 16 volts. So that's the potential difference across this resistor. Does it make sense? Look, potential drop across R5, 8. Potential difference across R2, 3, 4, 16. If you add 8 plus 16, of course, you're going to get 24. That's what we had in the first place. Okay, so now the next step, this one. So from this circuit to that circuit. So now let's reveal what inside of R2, 3, 4. Okay, I'm probably write my bridge here, right? So now this resistor replace these two resistors, connected in parallel. What is the same for the parallel case? Potential differences. Right? Delta V across R2, 3, 4 must be equal to the potential differences across R1 and R2, 3. So let me write then this. So delta V, I'm trying to estimate the amount of space, right? Okay, delta V 1, 2, 3, 4, it's this. Okay, let me show you that this value comes from here. Right. Equals to potential difference across 2, 3, 4, and potential difference across 1, and it is equal to this 16 volts. Right, 16 volts. Okay, so that's the bridge, which allows us to move from here to there. And now we know the potential difference across R1. We know the value of R1. We can find current flowing through R1. So I1 equals to delta V1, this delta V1 divided by R1, right? So delta V1, of course, as I said, it's from the bridge. R1 is 8, so 16 over 8, 2 amps of current. Am I right? Let me check. Yeah. And then, of course, now we can find current through this resistor R23. I234. So that's the potential difference again, which comes from the bridge, divided by R234. R234, 8 ohms, 16 over 8. Again, 2 amps of current. Actually, these two guys have exactly the same current flowing through them. Right? So now we're done with R1, but again, inside of R234, we have plenty of information. Right? Okay, so now we can move one step further. So now inside of R234, we have these two resistors connected in series, right? Connected in series. In series, currents are the same. Currents are the same. So I can write that new bridge currents are the same. So this current I234, I234 equals to I4 equals to I23 equals to 2 amps. Actually, first, let me check that the number are the same. Correct. Yeah, 2 amps. Yeah, that's correct. So that's this bridge. And now, again, we should be able to find the potential difference across the resistor R4, because now we know the current, we know the value of R4, it was given, so potential difference. Delta V R4 equals to R4 times I4. Right, R4, 4 ohms. Current, 2 amps. 2 times 4, 8. 8 volts. And now potential difference across R2, 3. Potential difference across R2, 3. Of course, it will be R2, 3 times current, which comes again from the bridge. So this 4 ohms times current 2 ohms, again, potential difference, the same, 8 volts. Again, 8 volts. And so now the last step. Inside of R23, we have these two resistors, R2 and R3. So the final push. All right, so wrong bridge. So this guy replaced two resistors in parallel. Potential differences are the same, right? Potential differences are the same. Potential difference, this 2, 3, now will be used in the bridge, of course. All right, so delta V 2, 3 equals to the potential difference across 2 and potential difference across resistor 3, and it is equal to 8 volts. So that's above this, that's the final bridge. And now we should be able to find the rest. Now, potential difference we just found. Resistance is given, so we can find current flowing through the resistor R2. So I2 equals to delta V2 divided by R2. So 8 volts. Divided, where is my R2? 6 volts. Now, finally, the numbers are not nice. So 8 over 6. So it will be 8. Okay, 8. No. 8 over 6, right? R2, 6. Yeah, so we can cancel by 2. So it will be 4 over 3 amps. 4/3 over current. And so now finally, I3. So delta V3, again from the bridge, divided by the value of R3. Voltage 8, R3 12. 8 over 12, again you can simplify, so by what? By 4. So it will be 2/3. 2/3 over amps. Okay, finally. Done. Of course, I'm not very likely that I can give that many resistors, right? But you see, once you know the idea, philosophy, it doesn't matter how many of them you have. You can just keep rolling, rolling, rolling. Everything is connected, right? Interconnected nicely. Again, it's one of those pieces which I like in this book, how he arranged these problems, this type of problems. And for equivalent capacitance, similar story, just need to use different charges, the same, or potential differences, the same in the proper places. Yeah, it looks depressing. I agree with you. Right. Okay, again, I will send to you this. All right. Okay, capacitors, one example will be in my notes. All right, I think it was in one of my quizzes from the past. Can I start erasing this? Okay, if you're not objecting, then I will start erasing, although I... So this was number 4. So the next one is very simple problem. I would say trivial, and most of you agree with me, but let's just refresh it quickly. So number 5. So we have a cylindrical wire of radius 2 millimeters. Current is given. Okay, let me draw this situation. It will be easier than just saying in words. So let me make it a little bit bigger. All right. So basically now we are in the current. All right. So this is our cylindrical wire. Radius is, okay, you know what? I will use r small for a radius. R equals to 2 millimeters. Because we're going to use resistance, that's why I switched to r small to denote radius of the wire. Right, so then it is, we know that the potential difference across this wire is 2.7 volts. Oh no, 3.7, sorry. So potential difference across that wire is 3.7 volts. Then the length of that wire is L, right? L small, yeah. 46 meters. Okay, it's better. Probably it's just a spool, right? Not just a straight wire. Of course, it's a spool. 46 meters. And so current deserve red color. So current I is 2.5 amps. So what do we need to find? Basically, the question can be stated, find the material. And most likely, I would, of course, find the proper numbers so that everything would match. And I would ask, what's the material of this wire? Is it made of aluminum, gold, copper, tungsten, molybdenum, right? Of course, it can be any piece of metal. But the problem says, find resistivity. Again, you remember, if you know resistivity and they open the book, right, reference book, you can find which material and which alloy used, right, to build this, to make this resistor, right? So let's find just resistivity, raw. But of course, I would state, find the material. Right, so what? Resistivity is in the expression for the resistance, right? And we have a proper shape, right? So geometry is basically given, right? And unknown will be in the expression for the resistance. So let me write, so first find rho and remind resistivity. And I hope you still remember, right? So what's the difference between resistance and resistivity? Resistivity, it's a parameter describing a material. Gold, tungsten, molybdenum, copper, right? A resistance, it's a property of an object, which has some length, some diameter, and of course made of some material, right? Resistance, property of an object. Resistivity, property of a material. Right, so as a result, of course, we can use R equals rho L over A. A is the cross-sectional over a wire. Right? So radius is given, of course, converted to meters. Maybe I should do it immediately. 2 times 10 to the power of minus 3 meters. Right? So, of course, we can write it rho L divided by pi R small squared. You know what? Probably let me change the marker. It's still good, but it's getting kind of too bright. Light. Right. Contrast is getting worse slightly. Right. Okay, so yeah, unknown is here, right? And then, of course, we need to combine it with Ohm's law in order to connect what is given potential difference current, right? So, of course, now Ohm's law. So delta V, oh yeah, much better. R times I. Again, guys, if you feel like lack of contrast, okay, marker is getting too light. Tell me, right? Right, so we can write, of course, we can plug it, and it will be rho L over pi R squared times I. Right, so given rho, one unknown, one equation, problem basically solved, right? Again, that's our only unknown, so let's just solve it for rho. So rho will be equal, pi R squared goes to here, so it will be delta V times pi R squared divided by L times I. Let me check. Pi R squared delta V, yeah, of course. So if you plug numbers, again, this is in meters, I converted already. So you will end up with 4 times 10 to the power of minus 7. Oops, doesn't look like 7 ohms times meters. I looked at the table of the book, and it's not close to any of the materials, so that's why I don't. I didn't change the problem. Otherwise, I would say, so which material? Right. But since the problem is not arranged for a certain material, which is given in the book, information about which is given in the book. So, right. Okay, so it's straightforward. And again, problems like this, that's probably the, I notice, the easiest for students. Most of you on the exam do well. So this is something similar to this, again, using Ohm's law, equivalent resistance. Again, you can look in my notes. I'll skip it. Okay. So we played with these ideas, right? And now Kirchhoff rules, right? Kirchhoff rules, and then RC circuit, which I kind of missed, right? And maybe a few questions about power. And I'm not planning to discuss Ampere's law because nothing to review. We just yesterday discussed Ampere's law, first example, and then on Monday in my recitation classes, I don't know in your recitation classes, right? So maybe you already discussed that cylinder with a hole, but in my classes I will do it on Monday. So nothing to review. We just started discussing. Okay, so. This is
that unit ohm meters?
Yeah, ohms. That's my ohm. Omega.
Gotcha, thank you.
Probably you're not in my recitation classes. Guys in my classes, they are familiar with my weird handwriting. My letters.
Watching the world seems happy and young.
Okay, they're not completely.
Golden is the sun
Kirchhoff rules. Okay, I will grab my notes because now I need to carefully redraw the picture. And this is number 6 as far as I remember. Okay, blue ended up in my hand. Battery, resistor, then another resistor, then another battery, then goes here to this resistor, connect them like this, then over here, resistor, let me extend it even more, then another battery with this polarity. Okay, let me check this polarity. Yeah, correct. Then I will put another resistor over here and just like that. Okay, now let me label. This is EMF 1. This will be our EMF 2. This is EMF 3. Let me write those numbers. EMF 1 is 3 volts. EMF 2 and 3 are the same. EMF 3 equals to 6 volts. Then resistors. R1. You know what? Resistors I will write on the board. I mean on the diagram. All right. Now for this problem, I'm not going to starve for the space. Actually, it's very simple. Most of the resistors are the same. Okay, let me write them. Then it's easier. R1 equals to R2 equals to R3 equals to R4. Enough. So 2 ohms. And R5 is the only one which is different. 4 ohms. Okay, now let me show where those resistors are. So this is R1, this R2, this is R3, then R5, R4, and R5. Okay, so that's the situation. So preliminary steps. First, we need to identify a junction points and label them. So let me label which one. This is A and this is B. A, B. So second, between these junction points, of course, current must be the same. So in this branch, part of this loop, current must be the same. Here, current must be the same. And over there, current must be the same. So now let's label them and pick a direction. Again, don't think, don't sweat, all right, because you cannot guess which direction should be correct, or direction of current, because we have battle of 3 batteries, right, tons of resistors, right? No way, just pick a direction, right, solve with that direction, and at the end you can adjust those directions, because if your current happens to be positive, okay, you guessed it right. If current happens to be negative, okay, make a statement that your direction of your current was wrong. Actual direction is opposite. So I will look at my notes. So I picked this direction. This will be my I1. Then I2 will be here. I2 down. And I3, which direction? Okay, that way. All right, so this will be I3. Again, any directions. Don't try to guess. You will never be able, most likely. All right, so then next, you remember we needed travel directions, all right, in order to see which points are initial, which points are final when you cross this or that element. Right. So again, directions, in this case, it's up to you. Clockwise, counterclockwise, you have complete freedom. So I will use mine in my notes. So this will be my loop 1, travel direction, and this will be, again, I think the same. Yeah. So this is loop 2 travel direction. Okay, so all 3 preliminary steps are done, and now it's just a question of writing, remembering those rules. So junction rule. Junction rule. And you remember, according to that rule, if you have n junction points, then of course one junction point is not going to give you a useful equation. It's going to give you a redundant equation, right? So we have to write only, for example, equation for point A. So let's just use point A. For point A, all right, so currents in only I3 enters junction point A, and so it will be on this side I3 equals, so I'm just using this junction rule, all the currents in must be equal to the total amount of current leaving junction point, right? So I3 enters and I1 and I2 leaves. Right, so that's the equation number 1. Again, how many equations do we need overall? 3, because we have 3 unknowns, I1, I2, and I3. Right. And again, if the question is also about finding potential difference, in that case it's very simple. If you know I3, if you found I3, then R3 times I3, it will be the potential difference. All right, so now loop rule. Right, so loop 1, which is this. You remember my minor compulsion, I usually start from just before the battery. I just like when EMF stands at the beginning of the equation. Just for me, it looks good. But again, it doesn't matter, you can start from any point. So I'm starting from here, and according to the travel direction, I must go down across this resistor. Across this battery. So we travel from plus to minus. Rule number 2, which we discussed in the lecture. If you travel from plus to minus across the battery, contribution to the equation is negative. So here we will experience voltage drop. So minus EMF 1. Right. Then after this we go across this resistor. In this case, travel direction that way. Current direction also that way. Directions are the same. Rule number 3, again from our lecture notes, the contribution is negative. Minus current I1, resistor R4. So minus I1, R4. Right. So after this, we have to cross this battery. So we travel from minus to plus. Rule number 1, contribution is positive. So plus EMF 2. Then, after that, we have to travel through this resistor. In this resistor, travel direction up, current direction I2 down. So directions opposite, contribution must be positive. Again, it's a rule number 4 in our set of rules. So plus. Careful with currents. In this case, now we are dealing with current I2. Here we had current I1, but now I2. Another place for typical mistakes. So I2 R5, I2 R5, and then we have to cross this resistor finally, right? So in this resistor, current that way, right? I1 travel also that way. So directions are the same. Contribution must be negative. So it will be minus I1. And now we're back to current I1, because in this part of the loop, current I1 flows, right? So it's I1 times R1. And please, guys, carefully. Now you have to complete the equation. So you're back to the original point, and it must be equal to 0. I know tons of students, right now 30%, if not more, they will just write bunch of these terms without writing it is equal to 0. You have to write the equation, not just bunch of terms. Every time I'm kind of reminding, warning, right, and still every semester, right, tons of, it's just wrong, strictly speaking, right? So, okay, anyway, so that's the equation number 2. I should have moved slightly to the left the whole equation. Right. So now the last one, this loop, loop 2. Loop 2, again, I will start probably from this point to cross. Let me check which. No, I started across this battery first. Okay, it doesn't matter. It's just the order of terms is going to be different. Right? If you start from a different point. Okay, so let me start from this. So first, travel direction up. So you have to cross this battery from minus to plus. Rule number 1: contribution must be positive. Okay, I'm starving for space, so let me move slightly. So plus EMF 3, this. Then across this resistor, travel direction that way, current direction also. So directions are the same, contribution must be negative. I3 R2 minus I3 R2. Then we're going down this way through R5. Travel direction down, current direction now I2 also down. So both directions are the same, contribution must be negative. So minus I2, again now current I2, not I3. I2 R5. So minus I2 R5. Now we have to cross this battery from plus to minus. From plus to minus, so rule number 2, contribution is negative. Minus EMF 2. Minus EMF 2. Right. After that, we're going this way. And now the last element, R3. Travel direction up, current direction also up. Directions are the same. Rule number 3, contribution negative. Minus I3 R3. Minus I3 R3. And again, it must be equal to 0. So that's our equation number 3. Okay, so 3 equations, 3 unknowns. So again, I1, I2, I3, these are unknowns. Okay, 3 equations, 3 unknowns. The rest is algebra. You can use a calculator, you can use a brute force and do it manually, calculate it, right? But of course, we're not going to do it, and of course, I will most likely never ask you. I will just write down the answer and with interpretations. I1, if you solve it, you will get 0.5 amps. Current positive. It means that direction of this current is correct. Correct direction. Then I2 minus 0.25 amps. Okay, so absolute value is 0.25 amps, but minus means that assumption about this direction of current I2 was wrong. So I2 actually flows up, right? Right. Okay, so I can say that's wrong direction. Just tells us. So adjust it. So I2 is actually up. And the last one, I3, is also positive. 0.25 amps. So it means that this direction, we guessed it right. Okay, so again, most of students do it well, occasionally mistakes, right? Careful with these subscripts, right? And again, equals to 0, equals to 0, right? Don't forget about that. So you know what? Now probably let's discuss power quickly. RC circuit, you know what? I think I described it here enough, right? So I will just, you can read it by yourself. Right? Okay, let's just discuss power. And then a couple of conceptual questions now.
Today we all will grow kinder and better as men as we put all our strife away. and the men, the athletes standing proud and tall. The triumph and the tears, the sacrifice of years, they come today to risk it all.
A few lines, right? So now let's discuss power. Yeah, here it is, power. It's number 7 now. Right. So let's discuss power dissipated in elements. Right? So let's assume that we have this circuit. Okay, part A, let's say. So first we have a battery, right, EMF given, and we have a bulb. It looks ugly. No, I don't like it. I practiced before. I never used the symbol, right, of bulb, and still doesn't work. I will draw something like this. Okay, bulb. It looks better. All right, and then let's say here we have a switch, right, and here there is another bulb. Right, so let me draw it. Right, so another bulb, and it's all connected like this. So initially, both of the battery is healthy enough, strong enough, right? So provides enough potential difference so that both of these bulbs are glowing, right? Initially. So switch is open. Initially, the switch is open, right? And so it's an initial situation, right? Switch is open and both bulbs are glowing. So what will happen to these bulbs if we close the switch? Right. Switch is open. Both bulbs are glowing. So finally, final situation. What the switch is closed. So now we have to describe what will happen to the current. I mean, to the power dissipated, the amount of light produced by these bulbs. Actually, you know what? Even let's actually write expressions, right? So initial situation. All right. So we will have to discuss what power. This is bulb A with the resistor RA, and this is the resistor RB, right? So we need to compare powers, right? So power in case A and power in case B, right? So what will happen to the powers? Right? So initially, what will be the value of the current? How can we find the value of the current? Easily. Equivalent resistance. These two bulbs are basically connected in series. Not basically, connected in series, right? So equivalent resistance are RA plus RB, right? So initially current will be, it will be EMF divided by RI plus RB. And then, of course, we can write powers, right? So which expression for the power would be the best in this case, or is the best in this case? Bulbs connected in series. So it means that current is the same. And we know information about the bulb, resistance. So, of course, this formula will be the best, I squared times R, right, in order to get information about the powers. So P, which way I label it? PA initially equals, of course, will be I initially squared times RA, and power in bulb B initially equals to I current squared of the current times RB. So that's the initial situation, right? That's basically is given, but I just wanted to write in form of formula. So now final situation. So switch is closed, and of course, at this point, at this junction point, of course, the electrons are not crazy, and they're not going to go, they're not even try to go through this bulb, because basically it's like crashing through the wall, right? Getting through the resistance. Why would they do that if there is a here open door, right? So there is no any resistance. So of course, all the current will go through this, right? Bypassing this bulb. So this bulb, there wouldn't be any current. Current through bulb B is going to be 0, right? So finally, I through B will be equal to 0, right? Which way I wrote it? Just a second. Yeah, RB is bypassed. RB is bypassed. So current just is not going to flow through RB. So as a result, of course, power through bulb B in the final case will be 0. So no light. And in the bulb A, so now resistance in the circuit, right, much smaller. Okay, not much smaller. Before, resistance was RA plus RB, but now RB is out of the game, basically. Current flows through this circuit, so resistance will be only RA. So current will go up, right? So now I through bulb A will be EMF divided by RA, right? So of course it's larger than this, right? Larger than I initial. Right? And so the power through bulb A final case, it will be, of course, IA squared times RA, right? Of course, it will be larger than power in bulb A, which we had in the initial situation. Right? Very simple analysis, just carefully. Right? Just be careful, right? And quite simple. Okay, the second case, B, yeah, we'll skip it. It's also somewhat similar, right? Simple circuit, 3 bulbs, right? And we need to analyze which bulb produces more power. So now let's discuss one conceptual question about magnetism a little bit. Right? Magnetism we just started discussing, so there is no point of reviewing it. Right? It's still fresh in your heads.
High up in the sky, the Olympic one glows like the sun. Watching the world seems happy and young. Golden is the sun. Every morning.
Erase up to this point. So let's assume that we have 2 wires. We discussed similar in the recitation class, but let me approach in a slightly, raise a different question. So we have 2 wires parallel to each other, but current flows in opposite direction. And the same in the value of currents are the same. Okay, so it's I think it's number 8 now. So first, okay, let me grab my notes. So the first wire is here. Right. Current, okay, I will draw current later. The second wire, let me use green. It will be here. Okay, now currents. This current flows to the left, and this current flows to the right. And it's time to erase this. And the question is simple. So currents are the same, you see, II. Is it possible, and where, to have is it possible and where to have zero magnetic field, net magnetic field? Right? Of course, what we have, this blue wire creates its own blue magnetic field, green wire creates its own green magnetic field, and it will be everywhere. Of course, at any point, we have superposition of two magnetic fields. And the question the question is simple. Is it possible, and where, to have a zero net magnetic field? And obviously, there are three basically regions which must be considered, right? Above, in the middle, somewhere between them, not in the middle, between them, and below. Okay, let me state the question, right? Is it possible? Is it possible to have points? With B equals 0. Again, let me emphasize B net equals 0 for these situations. For this situation. Okay, so of course, net magnetic field can be 0 only if we have these two magnetic fields pointing in the opposite direction and the same in absolute value. In that case, of course, there will be complete cancellation and magnetic field can be 0. So let's search. Is it possible to have points like that? So let's start from the top and let's draw magnetic field, direction of the magnetic fields for each of this region. So let's start with the blue. So right-hand rule number 2, outstretch your thumb in the direction of the current and curl your fingers around the wire. So if you do that, above blue wire, we're going to have magnetic field. Blue magnetic field is into the board, crosses. So let's call this is wire 1, this is wire 2. So as a result, we'll have crosses, blue crosses here. Right, so that's B1. Then below blue wire, of course, magnetic field will be out of the board, dots. And out of the boards, of course, all the way to this infinity. So those crosses will be all the way to that infinity above the wire. Dots below. All right. So over here I can draw dot here, dot. So it's our B1 here. Okay, I can draw over there. Right. So all the way to that infinity we have dots. Right? So again, B1. Now let's do the same for the green wire. Again, so now outstretch your thumb in the direction of this current and then curl your fingers. If you curl your fingers around this wire, above the green wire, magnetic field will be out of the board dots. Right? Again, above the wire all the way to that infinity, we're going to have dots. Magnetic field will be represented by dots. So I can draw it here. So dot, 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 and of course over there even higher. So that's our B2. Here also B2. But below green wire, of course, dots will be turned into crosses. Right? Again, magnetic field now will be into the board, crosses. So cross, cross. So that's B2. Okay, so now we see directions, and now let's start analyzing. Is it possible to have zero magnetic field? In the middle. Okay, not in the middle, sorry. Between. In the middle, it's different meaning. Right? Between these two wires. Obviously not possible because directions of both magnetic fields are the same. If you have both magnetic fields in the same direction, cancellation is not possible. Right, so what I wrote, okay, I stated in this way. So between since B1 is parallel to B2, so B net is not 0. Actually, a vector is not even needed, right? So just absolute value, right? That's what we want. Right? Okay, so between wires, magnetic field, impossible for a magnetic field to be 0. Now above. Okay, now it looks like, okay, not it looks like, it is. Both fields are in opposite directions. B1 in, B2 out. Are we getting any points where magnetic field 0, net magnetic field? Yeah, they're in opposite directions, but what about their strength? Obviously, B1, blue, is closer, okay, if we take this, for example, this point is closer to the blue wire. So, of course, magnetic field strength B1 is going to be larger than the strength of the magnetic field B2, because wire 2 is farther away from the point where which we analyze. So B1 all the time is going to be stronger than B2. So although in their opposite directions, but there will be just a partial cancellation. There will not be a complete cancellation of the magnetic field, right? So because B1 all the time is stronger than B2 in that region. So as a result, again, magnetic field, zero magnetic field is impossible in that region. So let me write something over here. So since B1 is larger than B2 all the time for any point for that region. So of course, again, there will be only partial cancellation, but not 0. We're not going to get 0. So, B net is not 0. And now let's discuss below. So in this case, similar story. Again, directions are opposite, but now B2, green one, green magnetic field is going to be stronger all the time because we are closer at these points. We are closer to the green wire. So of course, magnetic field strength is going to be larger. So in this case, B2 is larger than B1. So opposite situation to that. And again, there will be only partial cancellation, but not complete. So the net magnetic field will not be 0. So let me write again. Since B2 is larger than B1, so B net is not 0. So in this case, there are no points where the magnetic field is 0. So is it possible? So the answer is not possible. But let me check the camera. Still rolling. Cool. All right. But what do I have to change in order to get at least 1 point or some points with 0 magnetic field? What do I have to change? I'm thinking about this. For example, I can grab this wire 2, right, and change the direction of current. Oh, no, just change the direction of current, green wire. Change the direction of current in the green wire. If currents are going to be in the same direction, in that case, in the middle between the wires, this magnetic field will be still represented by the dot, but the magnetic field, green magnetic field, would be described by the cross. So they will be in the opposite direction. And in the midpoint, their strengths are going to be the same, right? So only in that case, in the middle, magnetic field will be 0. Right? If you change the direction of current, for example, in this second wire, and then in the middle, the net magnetic field will be 0. Right? Okay, so that's how you should analyze it. Again, if you just draw dots and crosses, right, everywhere, and see analyze. The analysis is quite simple. Right. Okay, so I think at this point we can stop. Again, as I said, I prepared the problem about RC circuit. I think you should be able to read it by yourself, right? So again, you just need to find, it's a complicated bunch of resistors, bunch of capacitors, find an equivalent capacitance, equivalent resistance, right? In order to find our RC time constant, right? And then again, then you can find the initial current, and then you just need to find the moment of time when then that initial current gets reduced by a factor of 2. Very similar we solved in our recitation class, but this kind of a little bit bulkier, right? So you just need to first find equivalent resistance, capacitance, right? And just a few preliminary steps must be done, and then very similar. Okay, so you should be able to read it, right? Okay, guys, so if you have questions to ask, otherwise I'll see you next week.
Proudly in the sky, the sun shines like a gold medal.